Hi everybody. Today we get to talk about similar polygons. We've talked a little bit before about congruent polygons, but similar polygons are really where it's at. Much more interesting. And the first thing it asks me right away is, under what two circumstances are two polygons considered to be similar? And the thing we ought to know about similar polygons is the corresponding angles are congruent, equal in measure, and the corresponding sides, here's the kicker, are in proportion. That's going to be the clever part for us. And so we're going to consider that these two rectangles are similar. Aren't all rectangles similar? What do you think? Are all rectangles similar? I say, well, how about these couple of rectangles I just scribbled here? One of them could be 4 by 8 and one could be 2 by 10. And while these angles match up just fine, yeah, the corresponding angles are congruent. These sides are not in proportion. It is not true that 4 is to 2 as 8 is to 10. That's not valid. So no, not all rectangles are similar. But we're going to say that these two rectangles are. So I understand that the corresponding angles got to be congruent. They'd all be right angles. And it asks me to make a similarity statement here, which will depend on often. And it starts off by talking about PQRS, and that would be similar with ABCD, with rectangle ABCD. Find the scale factor. And what we got to do is look around and see a couple of corresponding sides. I see that this side is 12, and isn't it true that AD corresponds with PS? So it must be a ratio of 12 to 8. Because one of them has a side of length 12 and the other has a side of length 8. And I would tell you, it's probably going to serve us better if we reduce that fraction, that ratio. 12 to 8 is really a ratio of 3 to 2. That's the ratio, the scale factor, or the ratio between these two rectangles. It asks me to find the length of the larger rectangle, and that'll be pretty easy to do. I could say 12 is to 8 as the length is to the length, but I'm going to use that ratio of 3 to 2. It's going to make it a little simpler to work with. The ratio between the two rectangles is 3 to 2. The big one to the small one, and I want to know what AB is. That's the bigger one, and it corresponds to a side of length 15. So we want to solve that little proportion right there. You can hit it with a calculator if you need to, but I think I could figure that answer in my head. I think AB would have length. Well, 3 times 15 is 45, and 45 divided by 2 would be 22 and 1/2. 22 and 1/2 for the length of AB. And I did it by looking for a scale factor and using the scale factor to work a proportion. And then it goes on to tell me that if the diagonal of the smaller rectangle is 17, and when we get around to studying the Pythagorean theorem, we'll recognize that that would be true, that 8 squared plus 15 squared would give us 17 squared. It asks me, give the length of the diagonal of the larger rectangle. And what you should recognize is the diagonals are in the same ratio as the sides. It's going to be just the same ratio. We won't need to use the Pythagorean theorem there. We can just use that ratio. And we understand the ratio between the two rectangles was 3 to 2, larger to smaller. I'm curious about the diagonal of the larger rectangle. I'll call it BD. And I can compare it to the length of the rectangle of the smaller one, which was 17. I don't think I need a calculator for that either, but you hit it with a calculator if you want to. It makes me think that 2BD would be equal to 3 times 17 is 51. Divide both sides by 2, and I can get the length of BD. Really, when I say BD, I shouldn't put a segment marker on it when I just want to know its length. 51 divided by 2 would be 25 and 1/2. 25.5 would be okay with me. That's how long I think that diagonal would have been. Now, we're going to play with a couple of trapezoids, and we're going to play with more trapezoids than these, but check this out, too. I say consider the two trapezoids are similar and find the perimeter of the larger one. Well, I notice here that this trapezoid has these segments marked to be congruent. This is what you would call an isosceles trapezoid. And if this length is 10, then this length is also 10. We'll see more about isosceles trapezoids today, since we didn't get to see them last semester much. Turns out it's true that if a trapezoid is isosceles, then like an isosceles triangle, those base angles would have been congruent. We won't use that right away, but we'll use it soon. Asks me to make a similarity statement, and I don't think that you could agree with me that trapezoid ABCD is similar to, and how to show a little trapezoid right there. It's a trapezoid SRQP. That's a similarity statement. I think I got it right. Is it true that angle D goes with angle P? Yeah, I'm thinking that the angle at D went with the angle at P. And it asks me to find the perimeter of the larger one. I think I'm going to have to do a little scratch work on the side to make that happen. First, I got to find the ratio between these two trapezoids. I only know one side on this trapezoid. I know that SR has length 20. Who does SR correspond with? And that would be AB. So the ratio between these two similar trapezoids is 12 for the smaller one and 20 for the larger one. We could probably reduce that ratio 12 to 20 and make life a little easier. Since 4 goes into both of them, it'd be a ratio of 3 to 5. You don't have to reduce it, but it sure does make life easier if you do. And I'm going to use that ratio of 3 to 5 to figure out the perimeter of this larger trapezoid. I'm going to go for the lower base first. These are called the bases, the sides that are in fact parallel. They would have to be parallel if this is truly a trapezoid. I could say 3 is to 5. That small trapezoid to big trapezoid is the lower base 24 on the smaller one. Is the lower base PQ. And what I have to do is solve that proportion. And I would know the length of PQ. Let's see, 5 times 24 would be 120. Divide that by 3. You hit that with a calculator, but I think that would be 40. Hold that thought. I think I got PQ to be 40. I'll employ that right there. But what about this side over here? Same idea. Let's go back and use that ratio that we figured between these two similar trapezoids. It was 12 to 20, but 12 to 20 we reduced it to be 3 to 5. So I'm going to say 3 is to 5, small trapezoid to large trapezoid, as this length 10 is to this length SP. If I work on that, I'm going to get 50 going in this direction as I cross multiply. 50 is equal to 3 SP. Divide both sides by 3. We can probably make that happen. And SP would equal whatever 50 divided by 3 is. I'm thinking that's 16.666 on your calculator, but 16 2/3 actually. That's what this length would have been. This one would have been 16 2/3. But since this one is isosceles, and these are similar trapezoids, would this one also have to be isosceles? I'll say yes, it would. This would have also been 16 2/3. So if somebody wants to get the perimeter of it, and it does have to be for the perimeter of the larger one, I just got to add up some sides, huh? I had a side of length 20. I had a side of length 40. Now you notice this side doubles to become this one. Does this one double to become that one? Yeah, they better because they're in the same ratio. I'm just adding up the sides over here. Then I got a 16 2/3 and another 16 2/3. And I'm just kind of playing around, and I got 4/3, don't I? And if I add these up, I got 60 and 32. I guess that's 92. 92 and 4/3. That'd be 93 and 1/3. I was thinking that's kind of an ugly perimeter, that 93 and 1/3. But I got another way we can look at it. Let's see if we can agree with that answer. Shouldn't the ratio of the perimeters be equal to the ratio of the sides? It's true, it should. And in this pair of trapezoids, the ratio of the sides was 3 to 5. 3 is to 5 as... And what was the perimeter of the smaller trapezoid? And I can add those up pretty quick. There's 20 and 36, so that would be 56. The perimeter of the smaller one would be 56. And that should compare with the perimeter of the larger one. You hit that with your calculator, see if you get the same perimeter. I will. I'm going to do it with a calculator, though. I got it. Well, maybe I can do some of that without a calculator. 5 times 56, that's 280, is equal to 3p. Divide both sides by 3. Hey, man, how many times does 3 go into 280? Yeah, hit that with a calculator, but I'm thinking 9 times 3 is 27. Subtract, got a 1, bring down the 0. 3 goes into 10 3 times. 3 times 3 is a 9. Subtract, got a 1. Yeah, that's 93 1/3, isn't it? So it is true that we should recognize that the ratio of the perimeters is equal to the ratio of the sides. If we knew the ratio of the sides was 3 to 5, the perimeter should be in that same ratio. Find the length of the median in each trapezoid and compare the ratio. Now, at this point, you don't know what a median is, but let me verse you a little bit on that idea. When you have a trapezoid, which has a single pair of parallel sides, this side being parallel to this side would force this to be a trapezoid. The median is the segment drawn when you join the midpoints of the non-parallel sides. That would be an example of a median right there. And as you were trying to figure the length of that median, these are called the bases. This is an upper base and there's a lower base. I'm going to call this one base 1 and this one base 2. And what do you think the median would be? It's bigger than base 1, but it's not as big as base 2, huh? And actually, it is probably what you're thinking. The median is equal to the average of the bases. It would be base 1 plus base 2 divided by 2. Okay, so now I'm going to go back to this page and figure out the length of each median and compare the ratio between the two medians. That should go pretty quick and easy. Let's find the length of the median in this smaller trapezoid. And that'd just be 12 plus 24. Just add up the bases and divide by 2. 12 plus 24 divided by 2. You see that would be 36 divided by 2, and that one would be, the median would be 18. Now let's find the median on this other fella too. Base 1 was 20. Base 2 is 40. Add them up and divide by 2. It looks like 60 divided by 2, so that's got to be 30. Now let's compare the ratio of the two medians. What I'm thinking is the ratio of the medians should be equal to the ratio of the sides. One of the medians was 18. One of the medians was 30. Can you reduce that fraction? Sure I can, because 6 goes into both of them. 6 goes into 18 3 times, and 6 goes into 30 5 times, so it's a ratio of 3 to 5. So not only were the sides in the ratio of 3 to 5, the perimeters were in the ratio of 3 to 5, and the medians, this median right there, would have been having that length of 30. This median would have had that length of 18. They're also in the ratio of 3 to 5. All the corresponding parts inside the similar polygons will be in the same ratio as the sides. Let's play a little bit more. I say that these two polygons are similar, and we're going to work out and find the missing lengths of all the sides here. But first I got to get the scale factor. Can you find the scale factor here? I only know one side on this trapezoid, on this pentagon, isn't it? Yeah, that's a pentagon, and it has a side of length 15. Who would it correspond with? And BC corresponds with QR, so it must be a ratio of 15 to 10. And I hope you're saying, well, I'm going to reduce that because it's going to make life a little easier if I do. And you can reduce that ratio. It would be a ratio of 3 to 2. Large polygon to small polygon, a ratio of 3 to 2. That's our scale factor. It's also called the ratio of similitude. I'm going to call it the scale factor. And I'm going to go for the length that is AB right now. So I will say 3 is to 2, just setting up a proportion, as 3 is to 2 as AB is to the side that corresponds to AB, which I'm figured is that length 6, as AB is to 6. And I think I can get AB right out of there pretty quickly. It would be 18 divided by 2, so AB would have been length 9. This guy's got to be 9. I scout out this guy over here, and I'm thinking, well, I see that since these two sides are congruent on this polygon, those two are congruent, so it makes me think that these two would also have been congruent, because they are similar. They're identical in many ways. Angles are congruent, and the sides are in proportion. Has to be for CD next. Let's go in that direction. The ratio from polygon to polygon was 3 to 2. But I want to know the length of CD. Who does it correspond with? Yeah, that length of 6 right there, huh? And so, yep, we're going to get that same amount when I go for CD. CD is also going to be 9. You can tell we guys got that 18 divided by 2. Let's get ED then. This one. The ratio between the two polygons was 15 to 10. 15 to 10 we reduced to be 3 to 2. The ratio between the sides of these two polygons is 3 to 2. Going further with that, 3 is to 2 as, and I want ED. Who does ED correspond with? And pretty obviously it goes with the side TS. So as ED is to TS, and TS was 12, seemed like we'll get TS out of that pretty quick. 3 times 12 is going to be 36. Going to divide that by 2. Yep. 36 divided by 2, we have to make force T has to be 18. Let me get that right. Oh, that's ED is 18. I apologize. My error. ED is 18. TS corresponded to it, though. I'll be careful now as I find the length of EA. The ratio between the two polygons, 3 to 2. As AE from the larger polygon corresponds to PT. Isn't it true that AE corresponds with PT? And PT we knew to be 8. So I'm going to get AE just that away. 24 divided by 2? Yeah, AE ought to be 12. I wonder if the ratio of these pyramids, these perimeters, would be equal to the ratio of the sides, 3 to 2. Got to check that. I believe it would be truthful. Here's a more interesting question. Let's check out these couple of similar right triangles. Well, this one's a right triangle. Got a right angle right there. And this one's supposed to be similar to it. Got a little similarity statement. The angle at R, in the last position, corresponds to the angle at C. So that's a right triangle too. And in fact, if this is a 30-degree angle, I'm thinking that if the angle at P is 30, then the angle at A would also have been 30. I'll probably talk about those angles a little bit. So I'll bet you we can figure the other angles too. It wants me to do that right away, doesn't it? So angle C would have been 90. I know that because when any polygons are similar, their corresponding angles are congruent. The angle at C must match the angle at R. What about the angle at B? Well, the angle at B is going to match the angle at Q. Could we possibly know the angle at Q? Here we got this triangle. The angles ought to add up to 180. There goes 90. So these two have 90 to share, forcing this angle to be 60 degrees. And if angle Q is 90, well, what about angle B? And angle B corresponds with angle Q, so that would have been 60 degrees as well. And then it says, give the scale factor. Now, this is getting a little bit more interesting. I got to find sides that do correspond, and the hypotenuse of this triangle, 8 root 3, is going to correspond to the hypotenuse of that one. So to start off, I could say it is 8 times the square root of 3. The length of the hypotenuse here compares to the length of the hypotenuse there, just 8. I ask you, can you reduce that ratio? And why, yes, I can. 8 goes in the top and the bottom. This reduces to be a ratio of the square root of 3 to 1. Now that's kind of an interesting ratio. We have to play with that for a little bit. But it's not going to go away. That says the square root of 3 to 1. Give perimeter of both of these things. I'm going to have to find out the lengths of the missing sides. Now, you could stay with that 8 and 8 square root of 3, or you could use the ratio of square root of 3 to 1. Either way is going to work just fine. I'm going to go with the square root of 3 is to 1 as, now I'm going to go looking for, say, PR. Now, PR is on a bigger triangle. The square root of 3 to 1 is bigger triangle to smaller triangle. And I care about PR, which is on the bigger triangle, PR. I want to compare that with, well, who does PR compare with? And it compares with this one that is 4 root 3, doesn't it? 4 root 3. So I got to figure out, oh, I'm sorry, you couldn't see that. This is the proportion that I've written. We got to solve that for PR. Not terribly difficult, tell the truth. 1 times PR is just PR. But what about the square root of 3 times 4 square root of 3? Let me give you a little verse on that for a moment. When you multiply numbers with radicals, a square roots of b times c square roots of d, you multiply the outside guy with the outside guy, that'd be AC. And the inside guy with the inside guy, that'd be BD. That might be useful as we're doing this one. What am I multiplying here? Well, I'm really multiplying 4 square roots of 3 times 1 square root of 3. 4 square roots of 3 times 1 square root of 3. Outside guy with the outside guy is going to give me just 4. Square roots of, and the inside guy with the inside gives me a 9. Hey, I know the square root of 9. Square root of 9 is just 3. So this is just PR is equal to 4 times 3, and that'd be 12. Hold that thought. This length would have been 12. I got to figure out about BC as well. I know that these things are in the ratio of the square root of 3 to 1. I want to find out about BC. I see that BC corresponds to this side that is 4 square roots of 3. Should I put that on the top or on the bottom? Well, this is bigger polygon to smaller polygon. And that 4 root 3 is on the big one. I want to compare that to CB. And if I get that, I'll be able to figure out the lengths of the sides. So I got to solve this proportion. I ought to cross multiply. 1 times 4 root 3, just 4 root 3, should equal the square root of 3 times CB. Square root of 3 times CB. But I want to know what CB is, so I got to get rid of that square root of 3 right there. Let's divide both sides by the square root of 3. Here they cancel, and there they cancel as well. So CB is equal to 4. This length had to have been 4. So if somebody wants me to come up with a perimeter of these triangles, it'll be fun and easy. Now, some numbers you can add and some numbers you can't. This asks about the perimeter triangle ABC first. I can add that 8 and that 4. That'll just be 12. But this is a different kind of number, and it has to be separate. So this would be the perimeter triangle ABC, this smaller triangle, would be 12 plus 4 square roots of 3. Figure out about the perimeter of this triangle before I tell you about it. Let's see here. I'm going to add them all up, and this 12 doesn't have anybody to play with it, but I can add those two together, and that would be 12 plus 12 square roots of 3. I'm pretty sure that'd be the perimeter for that one. Thought just occurred to me that maybe we could do something kind of clever to compare these two perimeters. Recall that these two similar triangles were in a ratio of the square root of 3 to 1. Square root of 3 being the bigger number of these two. And let me compare the perimeters of these two. The perimeter of the bigger one was 12 plus 12 square roots of 3. And the perimeter of the smaller one was 12 plus 4 square roots of 3. So what I want to ask you now is that a valid ratio right there? And it's kind of interesting to check it out. Let's multiply the product of the means, this one and this one. That'll be kind of easy to multiply 1 times that. That'd just be 12 plus 12 square roots of 3. And then now let's multiply the extremes, this one and that one. First guy times the first guy, that'd be square root of 3 times 12. That'd just be 12 square roots of 3 right there, huh? Plus, then what about the square root of 3 times 4 square roots of 3? That would just be, there's a 1 right there. 1 times 4 is just going to be 4. And the square root of 3 times the square root of 3 is the square root of 9. And 4 square roots of 9, that's just 12, huh? So I ask you, are these things equal? And clearly they are. So, yep, the perimeters are in that same ratio of the ratio of the sides, square root of 3 to 1. I just got one more thing I want to talk to you about. I've kind of scribbled it right here. But let me just take you for a little walk about a couple of similar trapezoids. And then I'm going to give you an assignment like it. Trapezoid ABCD is similar to trapezoid PQRS in the same order. And trapezoid ABCD is isosceles. So I know that these two sides are congruent. But I also ought to be thinking this guy's also going to be isosceles. They won't be congruent, but these two sides will be congruent with each other. These sides are not congruent. AD is not congruent to PS. But the non-parallel sides are congruent in each of these. So let's find a perimeter of each trapezoid. First I got to find a ratio between these two trapezoids. I only know a couple of sides here. I got to find a side from this one that corresponds to a side of that one. And you consider that, and I think it's going to have to be 15. That upper base compares to the upper base of this one to 20. If you reduce that ratio now, it's going to make life easier later. That's a ratio of 3 to 4, isn't it? So all the sides and medians and everything should be in a ratio of 3 to 4. Let's use that to figure out more parts. What do you want to find out? DC first? Let's go there. 3 is to 4 as DC is on a smaller polygon, so it's got to go smaller polygon to larger polygon. DC was going to go in the numerator there, and 36 is what it corresponds with. There's lots of ways you can solve this. You can think, what do you do with a 4 to make it be a 36? Got to multiply by 9, so multiply this by 9. It makes me know that DC would have been 27. Hold that thought. This length would have been 27. You can hit it with a calculator if you want to. But I also see that this is an isosceles trapezoid. It tells me that it was. So this side must also be 12. Let's find this length. It'll be the same as that one, and we'll need to find those lengths before we get the perimeters. I go back to the comparison of the sides, 3 to 4. That's the comparison of the sides between these two similar trapezoids. And I use this 12 in this ratio. Should it be on the top or on the bottom? That's a small polygon on top to a bigger polygon on the bottom, and the 12 comes from the small polygon. So I think I can get PS that way. So give me the length of PS, everybody. And 4 times 12 is 48. Divide that by 3. PS would be 16. Yeah, this length would have been 16. But we knew that this one was isosceles, so by golly, this one's going to be isosceles as well. Also 16. So if people want to know about the perimeter, I'll do the perimeter of, say, trapezoid ABCD first. Let me write that out, ABCD. And I can add those up. I figure I get 24. Do it on the work on the side. 24 for those two, and let's see, that's 42, I think. 27 to 15 makes 42. Those add up to 66. I think the perimeter of the smaller one is 66. I'm going to go for the perimeter of the large one, PQRS. And I see 20 and 36, there's 56. And 16 and 16 is 32. And 56 and 32 makes 88. I'm just going to compare those couple of numbers. That's 66 to 88. You know what? 22 goes into both of them, doesn't it? 22 goes into 66 3 times, and 22 goes into 88 4 times. Man, the perimeters were in the same ratio as the sides. Probably you expected that to be true, huh? Yeah, we would expect that to be true. Find and compare the lengths of the medians in the two trapezoids. You remember a little bit about that, huh? There's the median that joins the non-parallel sides from midpoint to midpoint. And if I want to get that median, how would you get it? I got to keep this paper handy, but it would be 15 plus 27 divided by 2. The median is the average of the bases. 15 plus 27 divided by 2. Add those up, 15 plus 27, I guess that's about 42. Yeah, 42 divided by 2, that'd be 21, huh? That's the median in the smaller trapezoid, would have been 21. Let's go for the median in that larger trapezoid. Add the bases. 20 plus 20 plus 36, excuse me, and divide by 2. 20 plus 36, there's 56 divided by 2, that'd be 28, wouldn't it? So I think the median in this one, from midpoint to midpoint, would have been 28. And you might be thinking, look, it increases by 8 and increases by 8 again. That's true. Well, this one increases by 6 and increases by 6 again. That's always true with the medians in a trapezoid. But what's the ratio of those two medians anyway? Well, the smaller one was 21 and the bigger one was 28. Does that ratio reduce? Sure it does. 7 goes into both of them. It's a ratio of 3 to 4. By golly, the medians, the perimeters, and everything is in the same ratio as the sides, except the angles. The angles are not in proportion. The corresponding angles are congruent. It tells me here that angle S was 70 degrees. And I should tell you that in an isosceles trapezoid, the base angles are congruent. This pair of base angles would be congruent. The angle at R would also be 70. But it turns out the upper base angles are also congruent. Whatever this measure is, this one will be the same. And you could be remembering right now, when we have parallel lines, which we must have, these lines must be parallel if that's a trapezoid, and you cut them with a transversal, what is true about this pair of angles? This one and that one. They're not congruent. This one would be congruent with that one. These two angles are supplementary, aren't they? So if this angle were 70, the angle at P would have been 110. Well, if this angle is 70, what about that one? Same idea. That one also would have been 110 degrees. So I know all the angles in this trapezoid, but it asked me for the angles in the trapezoid ABCD. I think we can make sense of that. I'm just going to write it right here, the measure of angle A. Well, who did angle A correspond with anyway? It corresponded with angle P, didn't it? So measure of angle A had to be 110. What about the measure angle B? Yeah, base angles of an isosceles trapezoid are congruent. That would also be 110. What about the measure of angle C? You know so much about this stuff. Angle C is going to be the same as angle R. Angle R was 70, so angle C is going to have to be 70. And the measure of angle D, the last thing we got to figure out right there, going to be the same as the measure of angle S, also 70. Man, these are the four angles of that quadrilateral. Angles of the quadrilateral should add up to 360. Those add up to 360? I'm pretty sure they did.